In this video, we're going to be discussing polynomial and rational inequalities. So we're going to be solving equations that have inequality symbols and finding the x's that make this come true. So we're only looking in the one dimension, only on the x-axis, since there are no y's and we're not looking in that second dimension. We're only looking for the x's on this number line that will make this come true. It's going to be an interval of numbers, like a space between a certain point and another certain point and all of the infinite number of possibilities in between. There might be multiple intervals for some answers, and there might be none. And we're going to investigate all of those possibilities by going through these steps. The following steps for solving polynomial rational inequalities are as follows. First, write the inequality so that the polynomial or the rational expression f is on the left side and 0 is on the right side. If it's a rational expression, meaning a fraction, be sure that the left side is written as one single quotient. So what that means is rather than having a fraction plus another fraction is greater than 0, combine those two fractions into one single quotient. So combine those using common denominators. So that's the first step we're going to take here. It says to write everything on the left-hand side and set it equal to 0. So that means we're going to move this 16x to the fourth to the other side by subtracting it. And of course we're going to write this in descending order of powers, so we're going to go from the 6th degree down to the 4th. This is the function. Okay, this is the f that they're referring to in this statement. Write the rational expression f on the left-hand side. So this is f. Step 2. If the expression is rational, find the numbers on the left side where it's undefined. Well, it is not a rational expression since I don't have a denominator, so I don't have any exclusions from my domain. My domain is all real numbers. Step 3. Find the real zeros of the numerator and the denominator and divide the x-axis into intervals. Find where the graph is above and below the x-axis. So the first thing we're going to do to find the zeros of this particular graph is we're going to factor it and find where this actually equals 0. These have a greatest common factor of x to the fourth power. So when I pull that out, I'm left with x squared minus 16 is greater than 0. I can keep factoring further since this is the difference of two squares. This becomes x to the fourth, x plus 4, x minus 4 is greater than 0. This is fully factored form. So at this point, to find the zeros, I pretend that it says equals to 0 instead of greater than. Let's pretend this is an equal sign. So what would make this equal to 0? Well, obviously if x is 0, negative 4, or positive 4. So I'm going to have those three zeros for this particular polynomial. So I'm going to use these zeros to divide my number line into intervals. So we're going to have negative 4, 0, and 4 will be my zeros. Those are my x-intercepts. Then I'm going to test these 1, 2, 3, 4 intervals with test points to see whether the graph is above or below, meaning positive or negative. I'm really only concerned with the portions of the graph where the function is greater than 0, meaning positive. So we're going to have to test all of them for positivity or negativity. I don't really care exactly what the number is. I just want to know whether it fits the positive, which is going to be part of the solution of this inequality, or if it's negative, meaning it will not be a solution. So let's find a couple of test points. So the first interval that we're going to be looking at is this interval right here, which is from -infinity to -4. Then this interval would be from -4 to 0. This interval will be from 0 to 4. And this interval will be from 4 to infinity. Then we're going to use the test point. In this interval, let's use the test point -5. Okay, if we use the test point -5, we plug -5 up into this inequality right here, and we see if this is in fact positive or negative. Well, you can see since we have even exponents, this negative is going to become positive. So we could also check it with our calculator. So if I wanted to put this also into my calculator, I could do so. I would test the fact whether -5 to the power of 6 minus 16 times -5 to the power of 4. Did that wrong. Try that again. -5 to the power of 6 minus 16 times the -5 to the power of 4. And that becomes a positive 5,625. So since this is a positive 5,625, we get a positive answer. So the result, the sign of the answer, is going to be positive. And this will fit part of our solution since we're looking for only the parts of the function that result in something greater than 0. Any number I would have picked in this interval would have yielded a positive answer. So now let's go over here and let's test something in this interval. If I test something in this interval over here, let's test the number -1. When I plug in -1 into my calculator, all I really care about is the sign, but I'm going to use the calculator to help me. So -1 to the 6th power minus 16 times -1 to the 4th power. We get a negative answer. So this is going to be a negative answer. Since this is a negative answer, it does not fulfill the characteristics of this interval, because that would make this less than 0 or negative. So that is not going to be part of my solution. Let's test something in the interval 0 to 4. Let's test the number +1. So if I go back to my calculator and we test the number +1, I'm going to use the same entry I did last time and just make these positive ones. I get -15, which is a negative answer. And when you get a negative answer, we know that is not part of our solution. The last number I'm going to try is something in the interval from 4 to infinity. So let's try the number 5. If I try the number 5 into my calculator, we have 5 to the 6th power minus 16 times 5 to the 4th power. And we get a positive 5,625. We get a positive. Hey, that fits my interval. I want an inequality what makes this function greater than 0, and any single number, anything in this interval, will give me a positive result. Therefore, any number in that interval will fulfill this function being greater than 0. So if the function is positive, we know the function will be positive for any number in that interval. If it's negative, then it will be negative for everywhere in that interval. You're just finding one test point, but it will be the same thing, the same case for any number you would have picked. Now we're going to use this information to write the set of all numbers that will satisfy this inequality. Clearly, any number in this interval is going to fulfill a positive or greater than 0 answer. So my answer is going to be any number between negative infinity to 4, but also any number between 4 to positive infinity. So this is my solution. Now notice I did not include the endpoints, the 4s on the ends, because I did not have an inclusion, an underscore, or an equal to sign on my inequality symbol. Let's try one more. Here we've got another example, and we'll follow the same rules that we had at the top of the page. The first step says to write the inequality so that the polynomial or the rational expression is on the left and 0 is on the right. And then also make sure any fractions are combined into 1. So that part is already done. Step 2, if the expression is rational, write the numbers at which the expression on the left is undefined. In other words, find the domain. The domain is what would make this denominator 0. Well, you could see if I were to factor this denominator, it's x plus 2 times x minus 2. So since this denominator can be factored into x plus 2 and x minus 2, you can see that there are exclusions of negative 2 and 2 from my domain. Since I have two answers that are undefined in my denominator, therefore x can never be either of those numbers. So those are going to automatically be points on my graph that I'm going to want to check what's happening in between those undefined answers. I'm actually going to write undefined underneath it just so I don't forget. X can never be one of those, so I can never include either of these points as an endpoint. I'm also going to include any number that makes the numerator 0 as well. For example, if I set this whole thing equal to 0, what makes this 0? Well, again, we only look at the numerator because the only thing I care about that equals 0 is the numerator. It does not matter what's in the denominator. As long as the numerator is 0, the whole fraction is equal to 0. So what would make this binomial right here equal to 0? Obviously, I'll have a 0 then at negative 3. So that's going to be one other test point in my graph. Now I realize I didn't draw this to scale, but that's okay. So these are going to be my boundary areas. I'm looking at 2, negative 2, and negative 3, and those are going to be my boundary areas for which I need to test. So let's go ahead and test these intervals. The first interval I'm going to test is from negative infinity to negative 3, and then from negative 3 to negative 2, from negative 2 to 2, and then again from 2 to infinity. So those are going to be the 4 intervals. Then I'm going to test these particular numbers. Let me test any number in this interval, such as negative 4. When I test the number negative 4, I plug this into the original equation up here, and you can see that negative 4 plus 3 is a negative number, but when I square it, I get a positive. That's going to be divided by negative 4 squared is 16 minus 4. That's also a positive. So that gives me a positive result. That will indeed fulfill this solution set since I want all answers that are greater than or equal to 0. So this is positive, so this interval will be part of my solution. Let's test a number in this interval. Let's test the number negative 2.5. Again, I don't really care about what the actual value is. All I care about is what the sign is for this whole interval. I'm looking to see whether it's positive, meaning it's a solution, or if it's negative, it means it is not. So if we plug in negative 2.5 up in here, we get a negative 2.5 plus 3, which is negative 0.5, but when I square it, it becomes positive. When I put in a negative 2.5 down here, when I square that, I get a number roughly between 4 and 9, something around 6 or 7 per se. And then when I subtract 4, I get a positive number. So this will also be part of my solution. And again, if you don't trust yourself with the mental math, you can always use your calculator. Since this was a difficult one, meaning it's a decimal, we could always use our calculator to check. For example, negative 2.5 plus 3 squared. And then I'm going to divide that whole numerator by negative, I need another parentheses there, negative 2.5 squared minus 4. And you'll see we do in fact get a positive number. And that's what we resulted down here. All right, let's check a number in between negative 2 to 2. 0 seems like a good one to pick. So 0 plus 3 is positive. Positive squared is positive. 0 minus 4, well, that's negative. So this time I get a negative result, so this is not going to be part of my result. One more time in the last interval from 2 to infinity, let's test the number 3. So when I put 3 in here, I get 3 plus 3, which is 6 squared. That's a positive number. 3 squared is 9. 9 minus 4 is a positive number. So this is a positive result. So this time I have 3 intervals that all give me a positive or greater than 0 result. So now I'm going to write all of the intervals in interval notation. So I'm going to start at negative infinity, and then I'm going to go all the way to negative 2. Since both of these are positives, I can go all the way to negative 2. Now, do I include negative 2? Well, normally I would say yes, include the negative 2, because I do have this underscore. Negative 2 should be included since I have the underline, meaning we could go all the way up to it and include that endpoint. But however, negative 2 is not part of my domain. So because of this, because it makes my denominator 0, I cannot include that endpoint. Then I also include this interval at the end that makes this positive. For the same reasons that we didn't include negative 2, we cannot include 2 because it is not part of my domain. So this would be the interval notation of this type of question.